When you give a traditional large language model a multi-step objective, you force a massive volume of processing into a single motion. It attempts to draft a complex research report or deploy edge AI code with the exact same uninterrupted flow it uses to answer a simple trivia question. The model drafts an output based entirely on its internal weights. It does not pause mid-sentence to run a search, cross-reference a database, or verify a statistic before moving to the next paragraph. In agentic reasoning, we break the process into planning, checking, and adjusting phases, forcing the model to stop and evaluate. During this pause, the system triggers external tools, running searches, pulling data, and verifying claims before synthesizing a final answer. This modular approach drastically reduces hallucinations, but it immediately introduces a new engineering problem. As a developer, you now have to define the rules for how the system handles uncertainty, and those rules will dictate your API costs and your response times. You are left with a strict trade-off. You can optimize your agent to handle real-time surprises, or you can optimize it for predictable efficiency. You cannot maximize both at the same time. That trade-off is managed through two dominant architectural patterns: ReAct, which stands for reason and act, and plan and execute. The difficulty lies in the mismatch. If you apply a structure designed for predictability to an uncertain environment, the system hits friction. If you apply a reasoning loop to a repetitive static task, you see it in your API bill. To avoid that friction, we have to look at the specific performance data and uncertainty profile of the task you are trying to automate. This diagram illustrates the mechanics of the ReAct pattern. It forces the model into a continuous loop, generating a thought, taking an action, and observing the result. Each observation triggers a new thought, steering the next action based on what it just learned. Because the context updates continuously, the system is highly adaptable. If an API returns an error, or two research papers give conflicting statistics, the agent sees the discrepancy and triggers a search for a tiebreaker source. For straightforward tasks, this is highly efficient. A basic ReAct loop requires roughly 2,000 to 3,000 tokens and 3 to 5 API calls to complete an objective, keeping your cost down to about 6 to 9 cents per task. But scale this up to a heavy multi-step data analysis, and the ReAct loop starts to buckle and fail. The context window fills up with past observations, the agent loses track of the original objective, and task completion accuracy drops to roughly 85%. ReAct handles unpredictable environments well. But if your pipeline requires the exact same steps every time, running a fresh reasoning loop at every single checkpoint adds massive latency. This flowchart represents the plan and execute architecture. It separates upfront planning logic from actual task execution. You spend your compute budget at the beginning, calling an expensive model once to break the primary goal into a step-by-step checklist. Once the plan is locked, the system executes it linearly. The heavy model steps away, and individual tasks hand off to cheaper small language models or standard Python scripts. The vulnerability here is rigidity. If the source data format changes, or step 2 fails to produce the expected output, the lightweight executor has no ability to self-correct. The entire pipeline breaks. However, when the environment behaves exactly as expected, strict structural adherence allows this pattern to hit a 92% accuracy rate on complex tasks. Looking at this comparison chart, you can see the cost of that precision. Plan and execute consumes 3,000 to 4,500 tokens across 5 to 8 API calls. The maximum cost per task climbs to 14 cents. You are paying a premium to guarantee the structure of your output, betting entirely that your real-world data won't throw any surprises at your executors. Let's map these metrics to a production environment. Consider a developer building a real-time customer service chatbot that answers user queries and triggers simple account actions. The ReAct pattern fits this perfectly. The inputs are unpredictable, the task chains are short, and the system needs to return a dynamic response instantly, while keeping token costs near the 6-cent floor. Now consider an enterprise architect building an internal tool that extracts financial data from massive CSV files, runs specific calculations, and compiles a weekly summary report. Plan and execute is the required choice here. The 92% accuracy rate and guaranteed formatting are non-negotiable for financial reporting, easily justifying the 14-cent operational cost. Mismatched choices lead to a measurable drop in system value. For a chat interface, plan and execute adds unnecessary latency and cost for every simple response. For financial extractions, ReAct's context degradation risks the very accuracy the enterprise architect is trying to protect. Some tasks, like compiling an industry-wide market analysis or running a literature review, require both high complexity and high adaptability. This is where the deep research workflow comes in. This animation shows the hybrid structure. Plan and execute builds the global scaffolding, locking in subgoals, but nests a ReAct loop inside each execution step. If a step hits missing data, it loops locally, finds a tiebreaker source, and passes a clean result to step 4. You get maximum accuracy and maximum adaptability, but it requires heavy state management and the largest API budget to maintain. Recently, the industry has shifted toward reasoning models. These models internalize the thought-action loop directly into their base training. Instead of requiring you to write custom orchestration logic to coordinate tools, the model evaluates its own options, calls a weather tool, reads the result, and autonomously decides to call a booking tool next. This schematic highlights the reality of embedded reasoning. The model may handle the tool selection, but the developer must build the hard constraints around it. Your engineering focus shifts. You spend less time writing loops and more time meticulously scoping tool permissions, setting hard-coded dollar spend limits, and building logging systems to handle bad model calls safely. The goal is never to build the most complex agent architecture possible. The goal is to calculate how much uncertainty your use case generates and apply the absolute minimum amount of structure necessary to keep the system honest.